Okay, we're recording now. I thought it would be useful for you to be able to see the individual bits as part of a floating point number. So this program works with single precision. So let's enter 0 and see what we get. Okay, so take a look. The sign bit says it's positive. The exponent is 0. Which if you debias is negative 127. But because it's 0 in the exponent and 0 in the fraction, that means 0.
Can you explain what it means to be debiased by negative 127 or whatever?
All right. So this is actually a general lesson for you. Let me get my iPad going. And there's actually a good lesson here in practical matters, particularly appropriate if perhaps you might be working in an embedded environment. Let's take a look. All right, so the general question is, how can you do signed math if you don't have a sign? And there's a larger question is, which I'm only going to brush against, how do you do floating point using only integers? Okay, so the answer to the first question here is floating point exponents are an example of doing signed math without having a signed bit. So you map 0 to the smallest number, okay, and you adapt all bits on to the largest number, and I'm going to put a star next to that, and you assign the middle number to the roll of 0. So in the case of single precision floating point numbers, there are 8 total bits where the bias is 127. Okay? So when you see the value 127 as the exponent, that means the true value of the exponent is 0. When you see 128, the true value of the exponent is 1. When you see 126, the true value is negative 1. Okay, so going back to, well, let me just say very quickly, how do you do floating point without floating point numbers? And that would be to do fixed point math. And the idea is very similar, where you can assign some bits of your integer for what will internally be considered to be the fractional part. So for instance, let me give you a quick for instance. Let's say you want to represent hundredths. So you take your integer and multiply it by 100. Look at the bottommost bits and then divide by 100. Okay, actually, forget about the divide by 100. So let's say you have 3.6. Well, you don't store it as 3.6 because you don't have integer, you don't have floating point. So you could instead, let's say your multiple was 100, you could store it as 306. No, 360. Okay, knowing that that is your decimal place, but you're only using integers. Okay. Yeah, when I started, if we didn't have literally, we didn't have floating point. So this is how I would store values to represent fractions. And the fixed point in this case is the hundreds place. Okay. All right, now going back to Floatster, let's take a look at the value there. Let's run it again. Let's take a look at the number 1. So what is 7F? 7F is 127. So debiasing, the exponent is 0. The fractional part is 0. So how do you get a 1 out of that? Okay, the
It probably
fractional
has
part.
something to do. I was going to say it probably has something to do with the F that we see there.
No, that just means it's hexadecimal. So 7F is 127 decimal. So there's an implied, in front of the fractional part, there's an implied 1. So this is 1 to the 0 equals 1.
Oh,
Now remember, the exponent is in binary. So base 2, not base 10. So how about the value of 2? So that's that implied 1 to the raised to the base 2 first power. Okay, now let's take a look at 8. Okay, so there's 1 times 2 to the 3rd is 8. Let's look at 32. I should have made it an argument. 32. Well, that is 1 times 2 to the 5th. Okay. Now, what happens if I put in 32.5? Watch what happens. Okay, so there is a 1 raised to the 2 to the 5th, and you've got a fractional value, which is a 1 in the, let's see, how many, this is also hex, so there's 4 bits, 8 bits, 16 bits. So that's a 1 in bit 18. How about 32.25? The 2 becomes a 1. So there's a halves place, quarters place, a eighths place. How about 32.125? Okay, so the bit moved over 1 more place. So you've got the halves place, the quarters place, the eighths place. Now let me introduce to you, let's try, what would be 32, negative 32.1.5? I mean, 125. Negative 32.125. What's the difference between those two values? You see 32.125 and negative 32.125. What's the difference?
Sign is 1.
Exactly. That makes the whole outcome negative. Good. And now let's try these two special values that I put in. By special values, I just have an if statement that says if the value you put in is -100, use that to cause a divide by 0. So let's put that in, -100. And check this out. It has a special value for the exponent of FF. So exponent FF is not allowed. It means something special. So take a look at INF. Something divided by 0 is infinite. So there's an actual bit that says this is infinite. And it's defined as having an exponent of FF and a fraction of zeros. That means the number that you tried to compute turned out to be infinite.
Could you try an input, please?
What?
Would you mind trying an input?
Oh, particular input? Sure, what?
I just want to try something that's not an exponent of 2. So like 24, 26. I just want to see how
Alright.
a whole number that's not an exponent of 2 is loaded. Okay. So yeah, okay.
Okay. Now let me show you not a number. So I'm going to enter this -200, which is a flag. It's not the actual value. This is going to give me the results of the square root of -1. Okay, so take a look at the difference between, I'll run this one again. Take a look at the difference between two of these last two. The one that has, so they both have exponent of FF. That says something bad. So a regular number will never have an exponent of FF. That's reserved. The difference between infinity and not a number is infinity has FF, all the bits turned on in the exponent, and has a fractional part of 0. Whereas not a number has exponent of FF, all the bits turned on, and has a non-zero fractional value. That means not a number. Okay, so having seen the output, let's take a look at the source code to this.
I have a question.
Yep.
I think I'm sort of confused on when it did the output for 24.
Mm-hmm.
So it said,
let me just jump in. The confusion is probably you're thinking about it in base 10. You got to think about
I
it
don't
in
think
base
I
2.
am. So it said that the exponent was 4, which 2 to the 4 is 16.
Mm-hmm.
And then the fractional part was, I don't quite remember actually, like 0, 0, 4. Do you think you could?
It was just 0, 4. 4 in the
0, 4?
second place. Yeah.
So that it goes, is it 1/2 and then 1/4?
Yeah, half, quarter, eighth, 16th.
So this would be like 1/4 times 2 to the 4, which is not 24. Because that'd be 16 divided by 4, which is equal to 4.
Okay, let's see the number.
Maybe I'm just doing something dumb and I don't know what's up.
So think about this in, all right, first let's look at the fraction because that we can deal with. So 1 and let's see, there are 23 bits, is that right, of fraction? let's see, I'll calculate it. 23 plus 1 plus is 24. And then what am I showing you? I'm showing you the wrong screen, but I caught it myself, so I get credit for that. So 23 plus 1 is 24, and 8 bits for the exponent is 32. Okay, so 23 bits. There's 4, 8, 16, 20, and then a 7. So that is 1, 2, 3, 4, 5. So 5 times 4 is 20. And then 1 times 3 is 3. That's 23 bits. All right, now let's take a look at the output. Get back to the output. Okay, so 1, 2, 3, 4, 5. There are 1, 2, 3, 4, 5 zeros from the right. So this is going to be 0, 0, 0, 0, 0, 5 zeros. And then the 4. Now let's turn that into binary though. So what would a 4 be? That would be 0, 1. Nope, sorry. The
Are you trying to be writing something on your drawing pad again?
see, I missed out. I still haven't done it. Okay, thank you. Okay, so that 4 is here. Okay, the fractional of 4. So let's see. This is the halves place. So 1.5 times 2 to the, what was it, 4th?
Well, why do you say 1.5?
Because of the implied 1.
Implied 1.
Right, so consider scientific notation. Isn't there always a 1 digit before the decimal place?
I don't. We can have 0 point something time.
Right, but 0.5 in scientific notation,
Oh
notation
yeah, you're going to.
would be 5 times 10 to the minus 1. That's 0.5.
So essentially, there's this extra 1 plus that fractional bit.
Correct.
Okay, I think that makes sense then.
Right, so,
It's going to be 16 plus 8, which is equal to 24.
hey, good, it worked out.
Nice. I was confused. Thank you.
Cool. All right. I'm glad when it does work. Okay. So let's take a look at the source code again so you can see how I did it. And guess what? There's a lesson in here. How many people have used unions before? Raise your hand.
Not I. I've thought about it.
Uh,
I was always sort of confused by them though, honestly.
I hadn't either.
Okay. Now, unions.
I don't think any of us have used them.
Ooh, that's why you take this course.
As in
Awesome.
like the mathematical operator union that I learned in discrete structures.
Yeah, well, it has just some semantics in common with that usage of the word. So let's take a look at how I'm using it. And then you see if you can tell what union does. So I've created a union, and it sure looks like a struct, right? Okay, now the members of the union are float F, which is 32-bit, and a 32-bit integer I. Now I'm reading into F, but then I'm using I. to examine the bits in F. So what do you
And do they
think?
represent the same value?
So yeah, what do you think that the union is doing?
So is it it's reading the bits but not interpreting them as a float, right?
Ooh,
Well, F is a float.
Yeah, but
it's taking it in as a
reading
float
I.
and interpreting it as the representation of the value in ints.
Okay. So that goes to the heart of what a union is. So in this case, I only have two members, but this does work for an arbitrary number of members, okay? And that reminds me, this might be one of Professor Mahoney's Java things. Did you do something with RGB?
I think
Which
we
class?
discussed about it.
In the one that they do Java in
Yeah, we use
Java course.
Yeah.
Okay, so follow me here. So a union. So all the members occupy the same memory. Okay? So as we say union, float F and int 32, uint 32 type I, what you're actually going to have is 32 bits, because that's the size of a float and a uint 32. So here's 32 bits. And when you refer to it as F, it's a single precision number. But when you refer to it as I, it's an unsigned int. And it's just raw bits, therefore. And they're both here. F and I are both here. How you interpret it depends upon which one you're referring to. Okay, now just to drive this home, I'm going to add another member. How about unsigned char C4? So when you refer to the union C0, that's one group of 8 bits out of I and F. C1, that's another group of 8 bits. So this is kind of like a way of dealing with that RGB project from the Java course, but done only using a real programming language. Because as we all know, Java is not one of those. Okay. Now, Cephas is thinking if I give him enough time, he's going to ask me question the following: which byte is byte C0 and which byte is C3? And yes, Cephas, it does depend upon the endiness.
See, it always comes back to bite you.
Oh
Get it?
yeah, literally. Okay, so the idea of a union is the members of the union occupy the same memory. And how you interpret that memory depends upon which of the members of the union you access. Sound good? Let's go back and look at the code. Now that we have unions out of the way. Let me add line numbers. Okay. So, What is line 27 doing?
That's a bit shift of 23.
Okay, so my goal is to get the exponent by itself. Flipping back to the iPad, let's refresh our memory of what a single precision number looks like. There is the sign bit. Then there's 1 bit, that's the sign. There are 8 bits for the exponent. And then there are 23 bits for the fraction. Now, you'll see in the code that I'll flip back to in a moment, you'll see that there's an instance of 23, and you'll see that there's something that looks like 8 bits. Okay, let's take a look at that line 23 again.
And doesn't bit shifting depend upon the endiness as well?
The endiness is when you break something down into bytes, that's when endiness becomes important, knowing which byte is the first byte.
Yeah, but
when
like,
you're
depending
dealing with an
upon
integer, the sign bit it's going to be, when you're dealing with an integer, a specific bit like the sign bit will be taken care of by the compiler for you. Because the compiler knows which end is the big end.
But if I were to try to do this in assembly, I would have to be aware, right? Because there are bit shift operations in there as well.
Yes. Yes, so fortunately I'm going through C or C++. All right, so how is line 27, oh, not line 23, line 27, how does line 27 work? Okay, so I'm taking the integer and I'm moving the bits to the left by 23.
So that means you've canceled all the 23 fractional bits. They're just
Perfect.
poof. And then you're anding it with all ones.
How many ones?
8.
There's your 8 bits. So what is that doing? That, dear students, is canceling out the sign bit. Right? Because the sign bit, if things were shifted down, right, the sign bit would be the bit coming before the exponent. So the exponent is 8 bits long. So we cancel out the sign bit by ANDing it with FF. And pay attention to this, I hope you are, because there will be a whole section of the course, not long, but a whole section, just on moving bits around. Okay? Let's take a look at line 28. Line 28 is going to get the sign bit by itself. So there are 32 bits where bit 31 is the sign. So shift it down by all of the bits except for the sign bit. And just because I'm cautious, I'll still AND it with just 1 bit.
What does the I think you literally just said it, but I did not process it. What does the AND do? The AND and then the hex.
So you're accustomed to seeing ampersand, ampersand, right? So that is a logical AND. So that takes trueness and falseness and produces a true value only if both inputs were true. a single ampersand, and also a single pipe, instead of pipe for OR, logical OR, a single pipe is binary OR, a single ampersand is binary AND. So let's take a, for instance, let me switch back here. So let's say we had a negative number, so there's a 1 under the S. And we have an exponent of 1, 1, 1, 0, 0, 0, 0. And then we have 23 bits of binary. I don't care what they are. Okay, so you see how these line up? Now, right shifting, did I say left earlier? So right shifting by 23 bits is going to result in excuse me. Okay. So what I just wrote are these bits shifted right 23 times. One, two, three, four. I have an extra 0. What's 1 0 between friends?
Probably quite a
Okay.
bit.
Yeah. Okay. So now the next instruction is an AND with FF. So that is 1, 2, 3, 4. No, I needed the 0. Yeah, okay, I did need the 0. So this was wrong. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Correct, I needed the extra 0. So ANDing with FF. So here's an F and here's an F. That means that's a 0. So going bit by bit, that's what the bitwise instructions do. Bit by bit, 0 and 1, 0, 0 and 1, 0, 0, 0, 0. 1 and 1 is 1, 1 and 1 is 1, 1 and 1 is 1, 1 and 0 is 0. So that AND instruction isolated the first 8 bits, eliminating the sign bit. Does that help, Jordan?
That makes a lot more sense.
Good.
Why not do a right shift and then a single left shift?
It's too complicated.
Well, the left shift isn't gonna,
Because I know they're like different conventions, but if you do the left shift, it should just make that other bit go poof. Right?
no, but this is, oh, but Cephas, this is in a 32-bit register. So shifting left by 1 doesn't do anything helpful. Of course, it shifts by 1, but it doesn't do anything helpful in this case.
Yeah, but would change something. Imagine like if this is the end and you did that left shift, it shouldn't the last bit go to 0? I think.
No, that's only the bits of, if you shifted left, the bit here going left would be lost, not the bit here. That's nowhere near the end. Okay, well, take my word for it.
So conceivably, if you like moved just these bits and then did a left shift, then it would work.
I'm not following you.
So like take these bits and put them in a new register per se, or put them in a new stack space, whatever C wants to do, such that it is just 11100. That's how what's contained. And this 1 starts at the end. So if I did a single left shift, now it's going to poof
Only
away.
if you did the left shift on an 8-bit value. Okay?
Okay.
So yeah, let's move on because, and trust me on this. If it was an 8-bit value, 8-bit register, left shifting by 1 would eliminate the sign bit. No, it wouldn't. Actually, even then, it would have to be a 9-bit register to make any sense of what you're saying. So let's move on.
Hold on real quick. So just to clarify, so the 0FF, when you use the ampersand, it's a comparison against the other values that we've off shifted to get that final boxed off value at the bottom. That's what the ampersand tells you to do with the 0xFF.
So yeah, the ampersand is a bitwise AND. So the rules are 0 and 0 is 0, 0 and 1 is 0, 1 and 1 is 1, and 1 and 0 is 0.
Okay.
Okay?
Yep.
And once again, it's done bitwise. So the first bit is ANDed with the first bit, second bit ANDed with the second bit, etc. Okay? Now, as an aside, the ARM architecture for completeness does have AARCH64 does actually have bit extraction instructions. So if what I wanted to do was, here's the sign bit, here's the exponent, and here's the fraction, I could either do it the way that I just did, and it would be a couple of instructions, but the ARCH64 instruction set does have an instruction that says, take these bits and only those bits and put them in a register. So that would be done without the shifting. Actually, it might even do the shifting internally, who knows? Okay?
That seems way easier.
Yeah. Okay. All right, so let's take a look at the second program. Or actually, let me go back to the code and see if there's anything else worth discussing. Yes, there is. You may not have seen this before. See that? Isnan, isinf. Those come to you in cmath.h or cmath if you're doing C++. Okay. And you may not have seen those functions before, but they are very important, especially if you're doing floating point in a mission critical set of software. You better be checking for isnan and isinf, because otherwise the patient's going to die, the plane's going to fall out of the sky, et cetera, et cetera, et cetera. There's a whole set of rules for mission critical life and death software, especially with regard to floating point. Okay. Okay. Once again, about floating point, let's take a look at the source code to the other program. And there's something interesting in here. Let's run the program. It's going to count from 1 to 100, and it's going to tell us which numbers are matched exactly in single precision and which numbers are only approximately correct. That's because There. So 7's not 7. 13's not 13. 16's 16. We already saw that. Okay. So not every whole number, in fact, not every number can be matched exactly in floating point format. Let's take a look at the code.
It doesn't even seem all that accurate. Like, if you're doing some serious math, like physical simulations, that's not that many decimal places.
Use double precision.
Oh, nice.
Why? So how does the computer interpret, like let's say we in C++, let's create a float and set that equal to 7. How does it know later that it's 7, or does it not return 7? Let me see what it does. I'm curious.
No, let's run Floatster. Okay. This is the binary value for 7, which would, let's see, would be 1, 2, 3, 4, 5, and then a 6. So that is, check it out. It is, let's see, I'm not on the right screen. So what was the exponent? The exponent is 2. 2 to the 2. And it's going to be, and there's a 6 there. So that is the quarter and an eighth. So quarter and an eighth is going to be 3/8. Okay, so that's the value of 7. So let me use a calculator. So 11 divided by 8 times 4. Okay, and I obviously did a miscalculation. 11 divided by 8, that's 1 3/8. All right, well, I got something wrong somewhere, but that's how it works. I was confident about getting that one right. Too bad. So let's see, this 7 would be the, so it's the quarter and an eighth. Yeah, all right. Oh, well, that didn't work out. Going back here, so take a look. So G is a float, and I'm taking the reciprocal of the reciprocal. So the reciprocal of the reciprocal should be the original number. But it's not. All the time. It's not all the time. Yeah?
Were you still sharing your screen?
Son of a bitch. Yeah, well, thank you. Thank you. I should get just used to this, accepting of this. So here's the reciprocal, and then the reciprocal again. All right. Does anybody see anything in here that sparks their interest?
Volatile.
Oh, have you seen that before?
No.
Anybody seen that before?
Yeah.
Well, of course, Cephas would have heard of it.
Well,
I mean, I
yeah,
know
yeah.
that word. I'll tell you that. I know the word. But
I
what?
think we all know the word.
I don't know exactly what it does. I would not put money on guessing what it would do.
Okay, so here, I'm going to do something. Volatile does a lot of things. And if you look up the actual standards document, it says volatile is implementation dependent. So the actual standards document gives no meaning, in no way defines volatile. Yet, we have this, it's a sexist statement, but we have this gentleman's agreement, okay? That volatile means certain things in certain circumstances. Let me demonstrate for you. Okay, so here's one use of the word volatile. Okay, I'll have to include IO stream. And, oh, am I on the ARM machine? I'd rather do this on the ARM machine. So let me back out of this. I would rather do this on the ARM. Okay, so vi foo.cpp.
It didn't update your screen share. I don't know why. You switched
Um,
Windows and Terminal, but
Yeah, because Apple. Does it work now? Yeah. Okay. Um, let's do this. Okay, what will this print? What do you expect?
99.
That's what I expect also.
I expect 99 lines from 1 to. Nah, actually, never mind.
Well, no,
Yeah.
it would print out 100. I lied. It wouldn't be 99. Because it would be,
Okay.
the loop would run when it's 99, but inside the loop it increases, so then it'd be 100.
Okay. Well, let's find out. G++ foo.cpp. Okay, now this is my ARM machine, so it's a little slower. All right, let's run it. Good, we got 100. All right. Now, let's take a look at the, I'm going to recompile it again, turning on all the bells and whistles of the optimizer. And I'm going to leave it as assembly language, okay? I'm teaching without a net here, so I hope it shows what I expect it to show. Foo.s. Okay, so let's try to find, there it is already. On this screen, do you see a loop? No, as Jordan's face indicates, there is no loop here. Let me V split. And there's no loop there. Where'd it go? On line 17, it is setting up to print the literal 100. So it went from, it completely stripped the loop and calculated, the compiler calculated what the correct answer is going to be and just put it in there. Okay? That's because I was in the optimized, highly optimized version. I told it to use -O3, capital O3. Now watch what happens when I add the word volatile here. Okay, that's the only change I'm making. And let me, did I save it? I'm not sure I saved it. There, okay, now I've saved it. And I'm going to do the exact same thing. And I wonder if VI will pick up the change. No, VI, warning, foo.est. Okay, so let me just, V split and edit foo.s. Okay, what do we have now? All I did was add the word Control W. Nope, Control W. There. Okay.
Not the same. Is that not the same code?
No, no, it's the same on both sides. Let me put back the foo.cpp. Okay, all I did was add the word volatile. And now in the assembly language, it got a lot longer and there's an actual loop in there. Line 23 is adding 1. So the word volatile has this unofficial, but completely uniformly adopted meaning of saying whatever is a volatile, do not optimize in any circumstances. So before, the optimizer said, hey, there's no side effects of that loop. So I'll just figure out what the end answer is. And isn't it faster to just jump right to the end than go through the loop? The word volatile says, I can't do that. The optimizer is not allowed to touch any code that has to do with a volatile variable.
So why would we do that? Like, why is being optimized and better and more efficient bad?
Ah, okay. That's actually getting into another lesson on how computers deal with hardware. So for instance, by hardware, what do I mean by hardware? I mean, like, how do computers deal at the hardware level with your mouse? How does it deal on the hardware level with your disk? And that's where volatile comes into play constantly. So let me show only the, let me show the, this thing. Okay. So this is a short digression to answer Jordan's question. So suppose here is your disk drive. Okay, yes, it has multiple platters. Okay, and that is connected to a disk controller. That is the hardware that runs the disk. Now that somehow is going to show up in memory. So this is what I'm showing you is memory mapped IO. So somewhere the disk controller is represented in memory. And when you read from that memory, you're reading from the disk controller. When you write to that memory, you're writing to the disk controller. So the memory is just a proxy for an actual piece of hardware someplace else. Okay? Now here's why volatile is important. So you might have a piece of hardware which is very dumb, and you tell it to do something, and then you have to poll to find out when it's finished. So, and the hardware is designed that when you launch the IO by writing to the register, by writing to the memory location, which stands in place of the hardware. Okay, then it's a dumb, it's a dumb piece of hardware, no interrupts. We haven't talked about interrupts. Then you have to wait for the IO to finish. And that is when I'm making this up, bit 6 becomes a 1. So in code, it would look like this. Let's say it's only an 8-bit device. So we'd have unsigned char star hardware. And let's give it the magical hardware address. So 17. This will fail, by the way. Jordan, did I guess the number you were thinking of?
No, it's just such a we're gonna do the magical number 17.
Yeah, 42. Okay, so I looked up in my hardware manual, and I found that the device I want to control has a register whose has a control register mapped to memory address 17. So I'm going to write to the hardware by saying star HW equals 29. So that 29 actually goes out to the hardware. And then then I want to read from the hardware. And I said bit 6, didn't I? So that would be ANDed with 0x bit number 6. So that is, there's just one bit, so that's 2 to the 6th. So that would be a 0 and a 2. Semicolon. Whoop. Semicolon. So this code is going to wait for bit number 6 to become a 1. Okay.
Isn't that a double ampersand?
No, it's bitwise.
But you're comparing.
Does this
okay.
help? Does that help?
I get you.
Okay, so I'm waiting for bit number 6 to turn on. Now, if HW was not declared, was declared like this, that loop would be eliminated from the optimized version of your executable because it has no side effects, right? So the only way to keep this code in your optimized executable code is to put the word volatile here, meaning that, once again, optimizer, don't mess with this variable because there's something going on that you're not aware of. Namely, the variable actually corresponds to a piece of hardware that the optimizer has no knowledge of. So this is the most common case of where volatile would be used. Now, it's important. It's important for you to actually know this because many of you may do a senior capstone that uses Raspberry Pi to control something, okay, or an Arduino. So when you're dealing with memory mapped I/O devices, it's absolutely critical that your optimized code actually does go out and touch the hardware and is not eliminated by the optimizer thinking it's doing you a favor. Okay. Any questions about volatile? Boy, visual mode in VI is just like the cat's pajamas. I could really have used this in 1979.
I have a question.
Yeah, what?
What is the purpose of using volatile in that other program than your approximation program? What is the purpose
This
in
one?
that? Well, no, that one isn't
okay.
the approximation one.
Yep.
The one where it tells you which ones aren't the same after the double reciprocal. That one.
Approximations.cpp, is that what it's called? No. What's it called again? Approximation.cpp. Nope. Okay, let me go find out what it is. Oh, it's not on this computer. It's over here.
Screen sharing. Sorry.
Yep, it didn't resume the share.
It really does not like terminal.
Okay, new share. Okay. Okay, so I put it there for two reasons. One, as an opportunity to tell you about volatile. But two is I realized that an optimizer could potentially eliminate something here. Now I'm realizing that it wouldn't have been the case because of this is a side effect. You know, so you can't get rid of this loop. That's originally what I thought. It's like, okay, I got to put this in, make sure I don't lose the loop, but I wouldn't have lost the loop because of the output.
Because the output requires a G.
Right.
But you're saying that you thought the computer might have optimized and just skipped the double reciprocal knowing it's supposed to return the same value?
Correct.
Okay.
That's exactly what I was thinking. Yeah, so actually, yeah, we'll leave it the way it is. Okay, so pretty cool. We just learned about volatile, and we learned about memory mapped I/O, and we learned about the approximations used in floating point numbers. Actually, you know, let's modify. I'm going to modify the program. And let's see what effect double precision would have. Okay, so I'll say And then I'll do the whole loop again. 1, 2, 3, 4, 5, 6. Whoops. 6, Y, Y. Okay. And now okay, so instead of a float, we'll make it a double. All right. And we got to get rid of this one. Okay. And now G++ approximations.cpp, and I'll save it instead of a.out, I'll save it -o-output to approximations. Okay, let's run it again. Isn't that interesting? Can you explain why they're different?
Optimization.
They're
Nope, no
Isn't
optimization.
double precision? That's why it's called a double. And the other one
Yes.
was single precision.
Yes.
Is
Actually,
that
I
why?
was
double
just going to say
precision is,
doubles are different from floats.
yep, so doubles are actually more than twice the precision of a float, but they are doubly sized. So check it out. In the first 100 integers, the float has all of those approximations, yet in doubles, there's only 4 in the same range. So with that extra precision, more numbers can be represented exactly. Second, notice the number of digits of accuracy. So Cephas was saying that 1, 2, 3, 4, 5, 6, 7 digits of accuracy doesn't seem like very much. So look at the double precision. Way more digits of accuracy.
I mean, in certain simulations, that's still not enough.
Well, then why stop at doubles? You can use arbitrary precision math.
Yep, you can. That's what things like Mathematica do.
Yeah, in fact, I think that would be BC. Huh.
BC.
Yep, isn't that interesting? That I haven't thought about this in almost 50 years, but when you mentioned it, I just, oh yeah, that's what it is. So man BC, the arbitrary precision calculator. Okay. How would you do arbitrary precision math? Are there instructions for it?
No.
No,
No,
of
we're going
course
to have
not.
to find them on the internet, probably.
Yeah, no, to do arbitrary precision math, you actually implement the math entirely in software, probably using strings. Right, so you actually simulate the math. And because you're using strings, you could do it with arbitrary length. So if you want 500,000 decimal places of accuracy, you'd use an arbitrary precision math package. Of course, you can expect the execution to be very, very slow.
Yeah.
Okay. Awesome. So that's the new knowledge for today. Let's do review. Okay, because I forgot to start the class with review. I was so excited to show you the little ditties that I wrote.
Can we review 2's complement by chance?
Sure. Okay. Let's see. Can we use the max calculator? So new share calculator. All right. And now I'm going up to the main menu and I'm going to say programmer. And it's still showing. Okay, good. All right.
Is this Apple Calculator?
Yeah, this is Apple Calculator.
You can do this?
Yeah.
I've never seen this. This is cool.
Okay, so here's your bit lines, ands and ors, nors, XORs, bit shifting by a certain number of bits, dealing with endiness. And you can do that in hexadecimal or decimal or octal. Okay, so we wanted to see, let's put in -1 in, I want -1, -1. Okay, let's just clear all that. Let's see, 0 minus 1. Okay, but let's see it in 2's complement. Okay, this wasn't as good a demo as I was hoping. So anyway, if that's -1, notice all the bits are turned on. So that's FF. See, is there any other way of improving? Show the thousands, decimal places. No, this wasn't as good an example. So I'm going to kill this and go to the iPad. Okay. So 2's complement. Okay, the reason to have it so that you get a single representation of 0. Okay, then how? But what's interesting here is converting to 2's complement is exactly the same as converting from 2's complement. So the same operation will undo itself. So let's take, so you take the inverse of the bits. You flip the bits and then add 1. Let's look at an example. So here's +1. So first step is take the inverse of the bits. Okay, so that is going to be okay. I'm going to move this over. Whoops, that's the wrong tool. I'm going to move this over here. Okay, so all the bits in the first case have been flipped. All the zeros are now 1s, and the only 1 is now a 0. Now add 1. Okay. Okay, and then this one also is F. Okay, so there's -1 in a 16-bit integer. Now let's convert it back again to +1. So let's flip all the bits in the F's. That becomes a 0, 0, 0, 0. Then add 1, and you get back 1.
I think my biggest question though is like, all right, so you have the 4 Fs. How does the computer know to interpret that as -1 instead of the super large number?
The computer doesn't know, but the compiler does.
Okay.
So the compiler emits the appropriate instructions for signed versus unsigned. Right? Now, as an assembly language programmer, you don't have a compiler. Because that's generating assembly language is the job of the compiler. And if you're writing your own assembly language, then you don't have the compiler to do that for you. So you would have to know that you wanted a signed versus an unsigned number. Okay?
Well, so if we have the sign bit, why don't we just, put one, so like we have 1 and it's 0x, whatever, and 1. That's 1. But then why don't we just add the sign bit making that -1? Why do we have to do 2's complement instead?
I understand what you're saying. And this is why.
Oh. Okay.
Okay, because without 2's complement, it would be possible to have, here's your sign bit, and then here's all zeros. And you could also have this. So there's 2 representations of 0, and that is very, very unattractive.
Okay. So what happens is basically about halfway through the single representation using the 2's complement, about halfway through, it'll switch from positive to negative. Like if you kind of wrote down all the possibilities.
Right, well, let's look at the difference between, let's just take char. So an unsigned char is 8 bits, and all 8 bits are part of the number. So you've got 0 to 255. There are no negatives. But if it's a char, then you've got the sign bit taking up one of your bits. So now you've only got 7 bits left. So there's your plus and minus. This is approximate. I'm actually going to be off by 1. Your plus and minus 127.
And that's roughly half of 255. Yeah. Okay.
Exactly.
That makes a lot of sense now.
This is a terrifically satisfying course for me to teach, because very often, things that you've taken for granted suddenly make sense of how they actually work. So this is a very satisfying class for me to teach. Things that you've always just taken for granted. Now all of a sudden it's like, oh, that's why it's the way it is. Meadow, do you have a question? No questions at all?
I have a question.
Yeah, but you always do. I'm talking to Meadow. So Meadow doesn't have any questions?
Nothing specifically right now.
Oh, well, thanks very much. You don't care how my day was? I'm kidding. Everybody's got a question. You can always answer, hey, what's your favorite ice cream? Okay, Thomas, how about your question? And it's
how do we write something like a array in ARM?
Like a pre-initialized array?
Yes.
Okay. Yeah, down in .data, you might have something like, well, what kind of array do you want?
Let's do like an array of. You can probably guess where this is going, but an array of like ints or something.
An array of ints.
Mhm.
So that would be, so some label, because you want to get to this array. So dot word, and then then a 32-bit value, and then dot word, and a 32-bit value, dot word, and a 32-bit value. So that's an array of ints.
Why do you use .word?
That's what 32 bits means in the ARM assembly language.
Okay. That just seems weird that you use word for like numbers rather than something else.
Well,
Oh,
then
aren't
let's take a
numbers
digression
like 32
and talk
bits?
about, let's talk about computer history. So you know what a bit is, right? And how many bits is a bit? Of course, one. That's a white horse question.
16. I mean,
Okay. So then you know what a byte is. Oh, what does bit stand for?
binary digit.
Correct. And a byte is 8. Did you know that there's a word for 4?
Or
Isn't it a nibble?
Nibble. Okay, there's also a word for 3.
Oh, I should know this. Oh, I forgot.
Jump.
An octet.
It's not an octet. That's an 8, right?
Yep, right, because 3 bits makes 2 to the 8th. Right, and then you know what a short is. So a short is 16 bits. And this is originally, for most computers, this is originally what a word meant. But then 32-bit computers became more common, and then 64-bit computers became more common after that. So the word, how many bits in a word has changed? It depends on the architecture. Now, this gives me an opportunity for a digression. So when I got to college and I took this course, where assembly language programming was taught, I was on a UNIVAC 1108, which had, follow me here, 36-bit words. 36. Now, what power of 2 is 36?
No.
Right? So what was a char on this machine? A char
It's
was
1 bit.
6 bits. So only the lowercase letters, the uppercase letters, and the numbers. And maybe a couple of like the period. So that was actually called, their character set was not called ASCII. It was called field data. Why? Because. So my first assignment, maybe I've told this story to you before. My first assembly language assignment was to read decimal and convert the field data to ASCII. So take a letter like A and turn it from its field data representation into the ASCII representation. That was my first assignment in this class. So I was so without saying this tongue in cheek, take any 5 smartasses that you know in class, right? Put them all together, and that was me. Okay?
There are no smart asses in this class.
Was?
Yeah, I'm
I
nowhere
don't-
near as smart as I used to be.
I don't
And
think
I'm far more humble.
with code, there's not really anyone who's smart. There's just someone who knows how to plan ahead and not completely fumble over everything repeatedly.
Okay. Okay, well, thank you. So what I would do, because I was definitely not a smartass, I was someone who planned ahead. The first thing I did when I got to college, and I found out I was going to be using an 1108, is I saw the people who worked at the computer center, they all had this little flip book of the internal instructions of the UNIVAC 1108. So in addition to how to use the CLI, the command line interface, it also had all the assembly language instructions. And it also had in addition to the assembly language instructions, it had macros in assembly language. So what I did is I noticed that there was a system supplied utility instruction, a macro, that converts field data to ASCII. So I handed in a project. I handed in a project that was like 4 lines long. And all of my classmates, hundreds of them, handed in 100, 200, 300 line programs. But mine was 4 lines long. And I'll never forget the grade that I got, because there was nothing wrong with my solution, but I did not get 100.
Because you didn't solve it the way they wanted you to solve it.
Right. And the grade was -5, so I got a 95. -5, quote, you ready for it? Too clever. So that was my first grade in this course, was -5, too clever. All right. So back to our classwork. Questions. How did we get here? Thomas asked, how would you build an array? And it would be if it's a pre-initialized array, it would have to be in the data section. And if it was an array of bytes, then you'd have just a dot byte, dot byte, dot byte, dot byte. If it was an array, maybe if it's smart enough, it would put 4 bytes together and call it a word. Who knows? Next question for review.
I guess, could I ask about, I'm a little confused. So I've begun working on P3. So I understand that like the buffer is going to be an array of char pointers size 10, but I'm confused where like the malloking 4096 bytes comes in and stuff.
Okay, so that static buffer, Jacob, is because you don't know how many characters are in a line until you've read it. So we just made a honking big buffer. The buffer is really big, and it's going to be super rare. Maybe it'll never happen to you. Then you fill up that whole buffer. But we had to pick a number, so we made it big. So with that big buffer, you assemble one line and then malloc another buffer, which is just the right size. Then copy the assembled string from the static buffer to the just the right size buffer. Does that help?
Yes. And then the char pointer array would point, each index would point to that just right size buffer.
Perfect. Yes. Now those will come and go. If our circular buffer is 10 items long, on the 11th item, we're going to have to free what was in 0 and reuse position 0. That's what makes it circular.
So I got a question about the strings that we're reading.
Mhm.
For some reason, we're gonna read up until we reach the end line symbol.
New line.
New line, yeah. Correct, or we're gonna read until we get a null pointer.
No, you're going to read until you get a new line
New
or
line
the end of the file,
or in the file.
or
What's actually the
you've used
byte?
up the whole buffer.
That
What
too.
is the byte sequence or int value for new line?
It is purely this. So it is in ASCII. So you have 0, which is null, and then the value of 1, that's actually control A. 2 is control B, 3 is control C. So the binary value of control C that you use to kill a program is a 3. Okay?
Okay, and new line is
And let me see. Let's see, control. Let's see, control J is, control L is a form feed, control J is a vertical feed. Carriage return, I don't know. You know what? I'm embarrassed that I can't remember this because this should be second nature to me, but I do have the excuse of being really old. So I'm gonna look up ASCII. Where is a browser?
whoa.
What happened? Hello?
We see that you're on the launch Zoom meeting page.
Good.
Line feed is 10.
Okay. So ASCII. And let's go here. And go here. And so where's the damn picture? Okay. So control A. All of these control characters do have a meaning. So control C, control D is the end of file. Control G. Control H is the backspace. J is the line feed. K is the vertical tab. L, I said, is the form feed. M is carriage return. And so there you are. There's J. So control J. Hey, you know what? I actually said control J, so I did get it right. I think I said control J. Oh, no, I said control J is a vertical. Okay, I conflated J and vertical tab. Okay. While we're here, take a look at this. Control S, often called X off, and control Q, often called X on. All right, so suppose those are actually useful things for you to remember. They work well for you in the shell. So let me go for a shell. And let's see, what's super long? Okay, suppose you had an infinite loop or something that was really long and you wanted to stop it so you can read what's on screen, but you don't want to kill it. Control C would kill it, right? So you can use Control S and Control Q to start and stop output from your program. So let's see, tell you what, hey, well, I know something. Find / print. Okay, so Control S, Control Q, Control C. Okay. So ASCII's pretty cool. So one of the other things that a person who planned ahead, not, i.e. not a smartass would write an infinite loop that output this character, Control G or \A. Go ahead. I can wait. Write a program that does nothing but output Control G.
All right, you pulled my hand.
Now, just when you do this, you might have your sound off. You might have other things configured so that the desired effect won't be heard. But when I did it in the old days, think about machines having actual physical bells that got struck by a hammer.
That's why you have all the bells and whistles.
Yeah.
Why is that a character in ASCII again?
Well, think about the teletype machine, right?
I
So
don't
the
sort of know what that is.
Okay, all right.
Nothing's happening.
Well, if your sound is turned off or other settings are set, you won't hear anything.
I take it I also might not need to be in Xcode.
You also what?
I'm in Xcode, so I should definitely not use Xcode.
Yeah. Okay, so Cephas, here's the teletype machine.
If you're presenting something,
I'm not showing it, am I?
no.
No, all we see is the buffer page. Now we see a machine.
Okay, that's a teletype machine. So something like this was my first terminal. Okay, now terminals like this would be in newspaper offices. And when a news story broke, the machine would start ringing a bell so that you'd go over to it, look at the output, and deal with it. So ASCII has a bell character because it would ring the bell of the machine.
I'm just not sure it needed to be put in a national standard, though. It seems like it could be programmed in a device-specific manner.
Yeah,
Well,
how?
some were made in different locations. How could you have a standard applied if it's made in, say, Germany when you are using the American standard?
Yeah, but ASCII is technically only for America. It's the American something, something, something.
While that is all true, it's an example of Americans saying it's our way or the highway.
There's Unicode, which is a superset of ASCII,
Yeah.
but that's technically the universal international standard.
All right, class is over. I only have, about 8 seconds to prepare for my next class, so I have to say goodbye. If you have questions, you can reach out to me over the weekend. Tonight is a barbecue, and I'll be guaranteed to be there at least for 30, 40 seconds. I'm kidding. I'll be there. Okay? Good night, everybody.
Oh, okay. I thought you were going to leave the Zoom.